Recall that we said t to the n is equal to the inverse Laplace of n factorial over s to power n plus 1. So if I ask you to calculate the inverse Laplace of 1 over s to the fifth, what are you going to do? You're going to identify what do you have and what is missing here. The inverse Laplace of 1 over s to the fifth can be written as, well, take a look at this. N factorial is just a number and it is missing from the numerator. So if it was written as 1 over 4 factorial times inverse Laplace of 4 factorial divided by s to the fifth, you're going to see the exact same relation here, which is equal to t to the power 4. So since we do not have n factorial on the numerator here, we can multiply and divide by 4 factorial. So this becomes 1 over 4 factorial, and you have the Laplace inverse of 4 factorial divided by s to the fifth, which gives us t to the fourth. So the inverse Laplace of 1 over s to the fifth is equal to t to the fourth divided by 4 factorial, which is 24. You can always check this answer. Check. How do I check? By finding the Laplace of t to the fourth over 24, which is defined as the integral 0 to infinity e to power negative st, and here we have t to the fourth divided by 24 dt. This guy, after doing the calculation, gives you 1 over s to the fifth power. You can always check that. Let's go over another example. Suppose I ask you to calculate the inverse Laplace of 1 over s squared plus 7. What we have learned so far, we learned that the inverse Laplace of, well, k divided by s squared plus k squared is equal to sine kt. Very well. So as you can see, you have s squared, s squared. You have plus, plus. K squared is 7. So k is equal to square root of 7. But we do not have the square root of 7 on the numerator. What are we going to do? We're going to multiply and divide by square root of 7. This is just a transformation. Remember that you can just transform the scalars without any change into the function that you have. So you get square root of 7 divided by square s squared plus 7. But this is mainly sine kt, or sine of square root of t. So we get 1 over square root of 7 times sine of square root of 7 times t. Let's take a look at another example. Make it interesting. Suppose I ask you to calculate the inverse Laplace of negative 2s plus 6 divided by s squared plus 4. Very well. What are we going to do? We're going to try to separate this and write it as inverse Laplace of negative 2s divided by s squared plus 4 plus inverse Laplace of 6 divided by s squared plus 4. Very well. So this is just a scalar. We can just keep this number outside the transformation. So this becomes -2 inverse Laplace of s divided by s squared plus 4 plus 6 times inverse Laplace of 1 over s squared plus 4. Now we have to go back to what we learned before. For example, we know that the inverse Laplace of k divided by s squared plus k squared is just sine kt. And we learned that the inverse Laplace of s over s squared plus k squared is nothing but cosine kt. So we need to find these similarities and then try to identify what k is and try to simplify it as much as we can. So take a look at the first inverse Laplace. The first inverse Laplace is similar to the cosine kt. So since k squared is equal to 4, k becomes 2. So your first inverse Laplace is nothing but -2 times cosine 2t plus 6. But here you have to be just careful. You need to have k on the numerator. So it means that it was 2 and this number was 3. So you get plus 3 inverse Laplace of 2 divided by squared plus k squared, which is sine of 2t. This is our final answer.